has hands-on hardware-level PCB analysis, developing custom Python and FPGA-based security tools. So looking forward to your talk, and please give a warm welcome to Lukas.
Yes, thank you very much. That's definitely more people than the last time I gave the talk internally. And I'm going to give a technical introduction to JTAG and ARM debugging interfaces. So I already warned some of you, there's going to be bits and bytes and there's going to be registers. But at least personally, I think it's really interesting. Maybe at the end you will too, maybe not, but I hope you will. I'll start with talking about JTAG. So what is JTAG actually? Because most of the time we just say, okay, JTAG is like a debug interface. Then I'll talk about the ARM debug interface, mostly because they're the only ones that publish their specs, so you can actually openly talk about it without an NDA. And then we'll take that knowledge and try and understand how we can use that to glitch a chip. Yes. Why would you want to spend your time researching this, or why would you want to attend a talk about this? So I don't know if you've ever decided to try and understand why the chip that you're trying to debug is not working, why your debug interface is not working, and then you scroll down to the reference manual and you saw this beast, and you're like, okay, shit, I'm out. I'll just, I don't know, go drink a coffee or something. And there's some people laughing, so. And then the second thing is I work as a pen tester, so we get ECUs from customers, and then one of the things that we do is we check debug interfaces. So we have to tell them, hey, your debug interface is locked, so you did a good job. And sometimes, like in this case, it's pretty straightforward. So here the debug software actually tells us your device is, or your chip is locked. But sometimes it's not that certain. So I don't know. In this example, is it actually locked? And sometimes they behave, when they're locked, they behave like they're broken, or it's just my test setup that's broken. So then you kind of have to go and try and better understand what's going on to be able to make sense of it. And I'm going to talk a bit about JTAG, and that's the IEEE 1149.1 standard. The second one is the ARM debug interface architecture specification. It's actually an older version, but it applies to a lot of the 32-bit microcontrollers, so it's still applicable. And then just a little bit about the ARM v7 architecture reference manual for some registers. But yeah, let's start with the test access port. So first, what is JTAG not? So JTAG is not a firmware debugging standard, which maybe might come as a surprise. I'm going to try this way around, because the original intention behind it is to perform automated tests on printed circuit boards. So your PCB comes out of the oven, and before you ship it to the customer, you want to check, are there any short circuits, or are all the interconnections functioning correctly? And this is what you might use JTAG for. So here we have two microcontrollers, and we have interconnections between them, and now we want to test them. So let's say we want to drive this pin here, and then we want to measure on this side. So we drive this too high, and then we measure here and see if the value that's here, if that's actually high as well. And I forgot to go grab something to drink. Would someone please be so kind and maybe give me, because I know that at some point I'll need something. Thank you. Yeah, so this is the original intention behind JTAG and what it actually allows you to do. And then manufacturers were like, hey, this is actually already there, and it's a physical interface, it's a piece of logic in our devices that's already there, so why don't we just use it for debug interfaces as well. Dankeschön. So just a tiny bit of vocabulary. The first thing is the tab. That's the test access port. And that's a bit of hardware, a bit of logic that's embedded into each microcontroller that supports JTAG. And the second thing is the JTAG boundary scan. And that's the operation with which I can drive pins or measure the value of pins of my microcontroller. So here we have these 3 microcontrollers, and each one has this little tab controller, which is a bit of hardware. And this is our, I'll just call it a debugger or tester. And then with JTAG, we can test these interconnections. All right, so yeah. Now that we know why it's there, what is it made of? So basically, if we want to break it down, JTAG is a system that contains 2 registers, an instruction register and a data register. And with the instruction register, I specify what I want to do. So for example, I want to drive a pin, or I want to measure a pin value. And then depending on what instruction I specify, the data register is what I communicate with to give data to this instruction or to receive data from the instruction. And that's, and it's in this sense virtual, because depending on what instruction I execute, I connect to a different data register. And the last thing that I have is the state machine. And the state machine is kind of the glue logic with which I can tell the JTAG test access port if I want to access the instruction register or the data register. And we can already see here the signals that I need for this. So we have the TMS signal, and with the TMS signal, I control the state machine. And then with the TDI and TDO, I push new data in, and I get data out. So TDI and TDO are for data, and TMS is controlling the state machine. And now we can already come back to this beast of a graph. And as I said, this test access port is controlled by the TMS pin. The TMS pin is a digital signal, so it can either be 0 or it can be 1. And we can see that every transition in this graph is either on a 0 or a 1. And the default state that we're in is the run test idle state, so that's where we start. And then, depending on what we want to do, we can either shift the instruction registers. So that's the first operation that we want to do. We want to tell it what we want to do, and that's this column. There are a lot of states in this. They're not really that relevant, but the same thing exists also for the data register. So whenever I want to change the value or read or write data for any of these 2 registers, I have to go through some of these states. And then I also have, the last thing that I have is the test logic reset state. And this only resets the test access port, but not the entire chip. So it's not like a system reset or a power on reset that I can do. Now, to make this more concrete, what instructions do I have? So what can I actually do with this test access port? There's one instruction that I always have, and it's the ID code. So when I program this instruction into the instruction register and then read out the data register, what I get is an ID code of the system that I'm talking to. And you can basically use that for introspection to determine if you're actually talking to the right chip. Then we have 2 instructions which are used for the boundary scan. And we can, I'm sorry, I forgot something. So here we can see the ID code always has a size of 32 bits. So that's the amount of bits that I get out of the data register. And with the sample, preload, and the access instructions, I can go ahead and drive individual pins or read individual pins. And this is why they have such large data registers, because every bit in this data register corresponds to a single pin of my chip. And so I can control every single pin of the chip. or read every single pin of the chip. Of course, this only happens digitally, so I can't read an analog value, but only a digital value because I only have a single bit for each. This is for an NXP IMX8. So here we have some instructions which are vendor specific, and you need some data sheets to know what they're doing. And then down here at the bottom, we have two instructions that we'll get to in a second, because they're basically what lets me implement a debug interface on top of JTAG. So what physical signals do I need? We've already seen some of them. One thing that we haven't talked about is the test clock. JTAG is a synchronous protocol, so I always have a clock, and everything that happens on a rising edge, and we'll see that in a second. I have test mode select, with which I control the state machine. And then when I want to input new data into the instruction or the data register, I use test data in, and the data that was in these registers comes out of test data out. Optionally, I can have a test reset, but normally that's not used because I have this special state in the state machine with which I can reset it as well, so I don't really need it. And then normally on a debug header or something that's on the PCB that I connect my debugger to, I'll also have a ground, a reference voltage, and a lot of the times I also have a board reset or a chip reset. And that's something you kind of have to figure out if you reverse engineer it. So we'll quickly look at each of the signals in detail, just a bit of detail. So the first that we have is the test clock. And anything, like I said, anything that happens on a rising edge. So every time, we can see this here in the logic analyzer output in this little arrow, this is a clock transition where something happens inside my JTAG test access port. And the first thing that's interesting is the TMS. So any state transition in my state machine happens on a rising edge. And we can see here, it starts out in this reset state, and then it stays in this reset state as long as TMS is 1. And then at some point, TMS transitions to 0, and then we can see on the rising edge, it changes to idle, and then it goes through this column of states to update the data register. And then we have TDI and TDO. And what's important to mention about these is that this is a shift operation. So when I update a register, I shift the bits in and I shift the bits out at the same time, one by one. So if I have a 32-bit register, then I have to do 32 clock cycles to push the new information in and to get the old information out. And I can't just read or write, I always have to do both because it's a shift operation. So here we see this in detail. We have the clock at top, then we have the TMS pin, which shows the state that the test access port is in. And we can see that we're in this shift IR stage, so there we can actually push new data into the instruction register, and we also get old data out. And we see here that on TDI, we write 4 bits of data into the instruction register, and we write the value hex A, and we get out the value 1. So we see that our instruction register here has a size of 4 bits, and we write this new value into it. Here we have a different example where we have a different chip, and we don't just write the instruction register, or we don't just shift the instruction register, but we also shift the data register. Here we have an instruction register size of 8-bit, and we write a C1. And then we do an update on the data register, and we see that we write the value 1B, and we also get out some data. And here we write 38 bits of data into this register. And what's in there now highly depends on the instruction, and what instructions are available highly depends on the microcontroller that I'm working with. Companies like ARM, they publish a lot of it, but some other companies, they really don't. So it's if you just take a signal analyzer and just look at this stuff, it can be really difficult to understand what's going on without a data sheet or a manual. But if we take a step back now, and we can kind of see what I mentioned is that JTAG and the tab is actually kind of like a physical and a link layer that I can use to communicate with my chip. So I can, as a manufacturer, I can just put any instruction that I want into this test access port. So of course I can use it for the boundary scan and for doing these PCB tests, but I can just put anything in there, so I can do whatever I want with it. And that's why, and it's already present, and that's why people or manufacturers decided to put the debug interfaces in there as well. And they're all different. I could also put Renesas on here. They have different implementations, they all differ, and that's why it's really difficult to talk about them. But they all rely on JTAG as the foundation. Okay, so now we've talked about JTAG. How does ARM implement a debug interface on top of JTAG? ARM calls this JTAG test access port, it calls it a debug port. And then on top of that, we have one or many access ports. And that's a logical feature. Normally, this is a memory access port. So this lets me look into some form of address space. So normally that's going to be the address space of my microcontroller with some flash, some RAM, some special function registers, and also some debug registers, which we'll get to in a second. But this doesn't have to be. So again, they're fairly flexible in what they do with it. But ARM specifies this as a memory access port. But like an access port doesn't have to be a memory access port, and we'll see with the NRF52, we'll see an example of what it also can be. And then it's important to mention that JTAG is not the only debug port that I can implement. So I already also have serial wire debug, which is a similar protocol, but only requires 2 signals instead of 4. So it's used specifically on chips with a smaller footprint and where I don't have as many pins available. Now, how does ARM implement the debug interface on top of JTAG? Basically, what we have is we have 2 new instructions. We have a debug port access and an access port access. And with these instructions, or with the first instruction, I can power up the debug ports, I can read status, and I can tell the debug port what access port I want to talk to. Or I can also abort transactions. And then with this access port instruction, I can perform read or write operations against the access port. And normally that's going to be a memory access port. So with this access port, I can look into the address space and read some RAM or read some flash, write some RAM, or change some registers. Now, these instructions, they always have a size of 35 bits, which we've seen in the table before. So I can always tell what do I want to read or do I want to write the register. Then I have 2 bits of addressing, which allows me to access 4 registers, basically. And then I can exchange 32 bits of data. So if I write something, I can always write 32-bit. If I read something, I can always read 32 bits. And this is what the debug port access looks like. So I have the TDI and TDO, and then I shift in these 35 bits, and then I can access, so I can read or write one of these 4 registers. And the important one here is the AP select register, with which I can tell it which access port I want to access, and then the control status register to check is the debug port okay, do I have any errors, or if I want to power up the debug port before I can do anything. And then the second thing is that once I've done that, I can access an access port. And again, I have these 35 bits. And then what's important is that these 2 bits of addressing that we have from the data register on top, we augment that with another 4 bits from the AP select register. So that gives me not 2, but 6. So 64 registers I can address, and then 32 bits of data. And the second thing that we have is through this AP selection, I can tell it what access ports, like which of the multiple access ports that can exist in my device do I want to access. So basically what this gives me, I can read or write 32-bit registers, or one of 64 32-bit registers inside this access port. And yes, it looks really complicated, but actually, how do we access memory based on this? This is a memory access port, so this is what the ARM debug interface architecture specification specifies as a memory access port. So it has these 64 registers, and if I want to do stuff quickly, then I want to use all of them, but if I just want to do basic stuff, then all I need is this transfer address and this data read-write. So let's say I want to read some value from RAM, then I write the 32-bit address from this RAM location, I write that in this TAR register. And then if I want to read this address, then I read this register. So I perform a read operation against my access port, and then what happens in the background is that the debug system goes into the address space, goes to the RAM, fetches this value, and then puts it in this register, and then I can read it. And the same goes for writing. So it's basically an abstraction that lets me access the address space. And that's actually, for basic stuff, that's actually all I need. Now I can basically see everything that goes on inside my microcontroller. So the only thing now that I need is to be able to control the chip, the CPU itself. So I need to be able to stop it, or step it, or read the CPU registers. So that's like the only main thing that I need to be able to fully debug it. And again, you've probably guessed it, I do that through register reads and writes. And this is what the ARM v7 manual specifies. Now the interesting thing is these registers, they don't exist inside my access port, but they actually exist inside the address space. So I go through JTAG, use the memory access port to access the address space, and then in this address space, I have registers with which I can control the CPU. And there's the debug, halting, control, and status register, and it has a bunch of flags, but the only ones we're really interested in are the halt and the step. So with these two flags, I can halt the CPU, I can step it, or I can let it resume processing. So just by writing these two bits, I can control the CPU. And now the last thing that I might want to do is I want to access the CPU registers, so maybe link register or program counter. And again, we have one level of indirection. We have two more registers. And in the first one, I tell it which register I want to access. So let's say I want to access the link register. And then I tell it which one I want to access. And then if I want to read it, I read this register. If I want to write it, then I write this register. And then the CPU will do this in the background, or the hardware will do this in the background for me. So it's just another layer of indirection. And the nice thing about the system is that I can implement this all of this myself. So if I take, let's say, some cheap debug hardware like an FTDI, like an Olimax or a FlySwatter, just some basic crappy stuff. Sorry. Then I can, just by doing these shift operations against the JTAG port, so just by shifting the instruction register and shifting the data register, I can, for example, implement all of this myself in Python. And it's a bit of code and takes a bit of reading, but just with this, I can implement my own debug system if I wanted to. I mean, I don't have to, because OpenOCD does this already for a lot of the ARM devices. But if I wanted to, I could. And that's really powerful, and actually sometimes is something that we use in pen testing. And we'll see that in a second why. Okay, yeah, so the last part of the talk is going to be a reproduction of the NRF52 voltage glitch. I call this a reproduction because it's not original work. This, I think it was done originally in 2021 or 2022. You can find it easily online if you want to look for it. But this was just for myself to to do a bit of learning into voltage fault injection. The target of this attack is the NRF 52840. It's an ARM Cortex M4 32-bit system on chip, single core, bit of flash, bit of RAM, and it has a debug port. Unfortunately, it's not a JTAG debug port. It's a serial wire debug port because it has such a small footprint that they don't that it doesn't implement JTAG, but only serial wire debug. But as I've shown in the slide at the beginning, to understand the ARM debug port, it's not really relevant if I use JTAG or serial wire debug. And of course, it has debug port protection. So I can lock the debug port. And then once it's locked, the only way to unlock it is to erase the chip. So I can erase the flash, and then I regain access to the debug port. But of course, everything that's inside of it is gone. They're used in the Apple AirTags, so they're quite an interesting target for people. There are two revisions that are interesting, or actually it's just one revision, that's the revision 2, and that's vulnerable to this fault injection. They released a new revision in 2022 to mitigate this fault injection. Okay, so now we come to the point where all the stuff that I said before actually starts to make sense, because this is an architecture of the debug system. So we have the external debugger here, and then it connects to the system through serial wire debug. So we just have two signals, but for our purpose, it doesn't really matter. So we have the debug port here, and then this debug port can connect to two access ports. And the bottom one, this access port here, it's the regular memory access port that lets me look into the chip, lets me control the RAM, lets me control the debug register. So that's how I do the actual chip debugging. And we can see here that it can be locked. So based on a value that it reads out of the flash during boot, we can tell it to lock this debug port, sorry, not debug port, but access port. And then I can no longer debug the chip. This value is read out during boot. And so there's not really a straightforward way to change that value, because the flash is, of course, contained inside the die of the chip. But I also have a second access port, and it's called the control access port. This is not a memory access port, and we'll see the register layout in a second. And with this access port, I can do different things. So I can ask it, hey, are you locked? And I can tell it to erase itself. So by writing a specific register inside this control access port, I can tell it to erase the flash and then to unlock the actual debug interface again. And this is what the access port, this control access port looks like. So instead of the 64 registers that I have for my memory access port, I just have 4 registers, and then all the way down here I have this identification register, which is again used for introspection and not really relevant. So I can reset the chip if I wanted to. I can erase it. I can see how it's doing with the erasing, or I can ask it, hey, are you protected or not? So is the AP protect status 0 or is it 1? So this AP protect status at register address C, it only has a single bit, which tells us is the protection enabled or is it disabled. Okay, so what is our goal? Our goal is to make the chip think that it should unlock the debug port, even though in the flash memory, so in the non-volatile memory, it says to be locked. So we have a device where the debug port is locked, and we want to look at what's stored inside of it. So we want to unlock the debug port. And what we see here is a oscilloscope trace from the boot process. And in blue, we have the reset pin. And at 0 seconds, this reset pin rises, letting the chip boot. And then in green, we have a GPIO pin. And here at approximately 90 microseconds, we see that it goes high. And this is the first thing that the firmware that I flashed onto the device does. So the first thing that it does is it pulls this GPIO pin high. So we know that in these 90 microseconds, it boots up the chip. Somewhere in between this reset and this GPIO pin, the device reads this locking status from flash memory and then decides to lock or unlock. And now what we want to do is we want to pull the voltage that powers the core. We want to pull that low to ground for a very short amount of time to manipulate this decision process by the device. So we have to find the specific point in time where it makes the decision to lock or unlock, and then pull the voltage low to determine or to try and convince it that it should unlock instead of locking. Now, where do we want to inject this value, inject this glitch? This is the chip, and this is the recommended, layout, how you should lay out the chip, and which capacitors you should place around the chip to make it operate normally. And we have this DEC1 pin, and that's a capacitor for an internal voltage regulator. So the voltage that is present here on this pin comes directly from the core. So this is what powers the chip, or the CPU, I should rather say. And this is where we want to apply the voltage. And if you ask yourself, why this one? Of course, it's trial and error, and this is not work that I did, but this is work that was done by the guy that originally did the glitch. So he figured out where to do that and where to best do that. This is the setup. So we have a small board with an NRF52840. And then here we have this little capacitor, which I removed. And then I have an SMA adapter and a little thin wire that connects from this adapter to the pad on the PCB where this capacitor used to sit. And this is still not the full setup, but we have the board here. Then we have the SMA adapter. The top one goes to the glitcher. I'm using a chip whisperer light. And the bottom one goes to the oscilloscope so we can actually observe what's going on. And then we have the debugger here, which is an All-MX. And it connects to the serial wire debug pads, which are on the bottom of the board. So before we come to the demo, what do we want to do? So this is a loop. We basically want to brute force the right amount of, or the right point in time and the right size of our glitch. And we do that in a loop until we find one that works. So for every iteration, we choose the new glitching parameters. Then we put the target into reset. And then we arm the glitcher. And then once the target comes out of reset, when we do so, the glitcher is going to wait the specified amount of time before inserting the glitch. And then lastly, we check this AP protect status register in the control access port to determine if it's locked or not. Okay. All right, so I did a recording because I actually thought about bringing the setup here, but it wouldn't have fit the table. I'll just basically walk through the recording. The first thing that I did here is to run OpenOCD with a full configuration file. And here we can see that OpenOCD, it's trying to establish a debug connection to the chip, but it says, yeah, hey, so this chip has the AP lock engaged, so I can't debug it. And it proposes that we use this nrf52 recover function, which erases the flash to regain access to the chip. So this is just, so to verify that it's actually locked. And this is me pointing that out. And now I rerun OpenOCD without the definition for the CPU. So that's just the definition of the debug port, not the access port, which lets me control it myself. If you're wondering now why it's not saying that it's not locked, that's not because I'm tricking you, but it's because it doesn't know about the CPU, so it's not trying to connect to the CPU, but only to the debug port. Now here we have the Jupyter Notebook. So in case I don't know if you've worked with Chip Whisperer, they do all of it in Jupyter Notebooks, and this is one that I adapted to the needs for the glitch. And what we have here at the top is this is AP protect active function, and this is what I use in the glitching loop to determine if it's actually active or not. Here I read this register, so this is register C and access port 1, which was what we saw in the architecture diagram before. And then if it's not 1, then it's active. So and if we continue, we see, now when I execute the, I'm going to show this, and then when I execute, we see it's active. So this is just to verify that the device is actually locked. And now I execute I show the glitching loop. So this is the actual loop that does the glitching work. So at the top, I specify the start offset, so where, like after the reset happens, where they want to start glitching. And obviously I picked an offset that's fairly close to where the magic happens, so we don't have to, just for the demonstration purposes. And then, so this is the X offset, that's the parameter that specifies how long to wait. And then the second parameter is the repeat. And that basically tells it how long the glitch should be, and we'll see that in a second. And the last thing is the tries. So for every offset and every repetition, I do 3 tries. And this is the actual loop. So here we have the glitch settings. We apply the offset and the repeat to the glitcher. Then we check if the device is alive. And then we first cut power to it because I realized that sometimes it's not really reliable. So I always cut power to the chip. Then I pull the reset low. Then I give it back power, which is going to cause it to stay in reset because the reset is still pulled low. Then I arm the glitcher, and then I release it from reset. And now then at this point, the glitcher is going to do its thing because it sees the reset go high, and then it's going to wait for the specified amount of time. And then it applies the glitch. Then there's just a bunch more stuff. And then at the bottom, we see, once I scroll down, we see that I check this function. So is AP protect active? If yes, then we count it as a normal try. And if not, we count it as a success, and we break our loop and stop testing. Because, of course, once we know that it's unlocked, we don't want to touch it. Like, we don't want to reset it. We don't want to cut power. Like, we just want to keep it the way it is and then manually check if it's actually unlocked or not. And now I start the loop. So I start executing the cell. And now we can see at the top where it actually goes through all parameters. So it goes through the offsets, and we start at 1500 offset. And then it tries, for each offset, it tries the repetition. and it does 3 attempts. And this is what it looks like. So in red, we see this the small spike, and this is where the glitch happens. So again, blue is the reset, red is the core line, and the green is our as the GPIO pin. And the spike has a varying length or varying depth, and that's because we try different glitch widths. So the wider the glitch, the more pronounced is this spike. And now, basically, all we have to do is wait to see if we find a good spot or we don't. And this is kind of the black magic around it all. And now we see that it stopped because I conveniently picked the offset. And we can see that we have a success. So the loop ran, it checked the AP protect status, and it realized that it's not 0, but actually 1. So it stopped. Now I go back to the OpenOCD window, and I restarted again now with the full chip definition, so with the CPU. And now what we can see here is that instead of showing us that it's locked, it's actually showing us that it found the CPU and that it knows that the CPU supports up to 6 breakpoints and 4 watch points, which is something that it doesn't that it figures out by looking into this memory access port. So it was actually able to read the debug registers inside the memory access ports, which is something that it could only do if the port is unlocked. So this is basically proof, if you want to say that the device was successfully unlocked. Yeah, so, and where is it? There it is. So yeah, I'm actually ahead of time.
Thank you very much for this great talk. Are there any questions from the audience?
Thank you for the talk. Do you happen to know what they did in revision 3 to protect against potential?
Yeah. So I don't fully remember it, but they basically changed it so that it's locked by default. So this register has a default value that causes it to be locked, and if you want to unlock it, in software, you have to, during boot, in software during boot, you have to write a specific other value to this register to make it unlocked. And again, I'm not entirely sure, but I think this is what they did. And now, that's not something that you can simply glitch, so you can't just glitch the value to something else, of course, especially if it's a 32-bit register. So I didn't try this. I actually, when I first bought when I bought the NRF52, I actually bought the revision 3 accidentally because I didn't know about it. And then during testing, I realized that something was wrong, and then I had to go and buy one that was actually still revision 2. But I haven't tried, just applying the same stuff to revision 3 to see if something falls out. But at least looking at it, I decided that, or I thought that this sounds a lot harder to glitch.
Okay, thank you. More questions? Okay.
Thank you for the talk. In the first half, you mentioned that you do sometimes explore other access ports.
Mm-hmm, yeah.
And what libraries are you using to do that?
So if you just want to, if you want to talk directly to the access ports, and then it's an ARM device, then I use OpenOCD. So there you can either, if it's a JTAG, you can tell it, okay, I just want to, just define the JTAG test access port, and then you can actually control the instruction register or the data register, and you can do everything yourself if you want to. But you can also, if it's an ARM device, you can also define it's what they call a debug access port, and you can define that, and then it knows, or then you can ask it, hey, this access port, what is it? So let me go back. So here we always have these identification registers. So for any access port, you'll have a value here, and that's how it knows what this is, and then it tells you a lot of information about it. So if you just want to do basic introspection, that's what you can do. So you can just define some stuff in OpenOCD and then ask it about the different access ports.
Are you scripting OpenOCD and TCL?
Not really, no. So I'm a Python guy through and through, so whenever I can, I try to abstract away anything else and then do everything in Python.
I can do the same.
Okay, more questions? Here's one.
In the recording, one could see the green line sometimes move to the injection point. Was it an artifact or?
Yeah, that's a good question. So sometimes what can happen is that it might be that the trigger for the oscilloscope was not correctly set, and then there was some jitter on the reset line that caused it to trigger on something else. So that's one thing. When I saw the recording, I was like, darn. And the other thing that could happen is that when the glitch is too strong, then it just resets the chip, and then you don't see this nice this nice example here where you have the glitch here at some point, and then you see you still see, although you have the glitch, you still see the chip boots normally. So then it's gonna have the glitch here, and then it's gonna reset right away. But this still wouldn't explain entirely why the green line is here, but it might have something to do with it. So I didn't really look into it, but normally that's because it resets.
Okay, thanks. More questions? Otherwise, thank you again for a great talk, and thanks for being here.
Thank you.